morning and good afternoon. Sorry to keep you awake this evening, but time difference is very hard for us. So and also thanks to Mehdi for the invitation and Attila as well. So let's start the presentation. I assume that you can see my screen. Okay, so I'll start with the title of Overcoming Black Box Pitfalls Through Soil Science Informed Machine Learning. So I'll explain later why I mentioned about this, whether this black box is a problem or not, right? So if we see the number of papers on machine learning, different kind of machine learning, neural networks and random forests on soil application, this is only on soil application. We can see that it's being excessive. It's been every day you see probably tens of papers being published on these various topics of using machine learning in soil science. And before that, I would like to get a little bit of a historical perspective that machine learning, or at that time it's called data mining, has been used since the late 1990s. And this is one of the examples by a colleague, Yakov Bachevsky. He's from the USDA in Beltsville. And he, at that time, there's still no open source software. There's still, you have to compile everything in Fortran or C to try to establish a relationship between what we call pedotransfer functions, the easily measured data. For example, we have the sand, silt, and clay, or bulk density, but we need to predict a water retention curve because we need to put it in a model to simulate available water capacity or water transport and so on. So this pioneering paper, and people are still doing it nowadays, are trying to use, probably one of the first to use neural networks. And as I say, at that time, that you have to really code the neural networks and optimize it and try different configuration, try different inputs. And at that time, I think one of the good example or important conclusion is that the authors, Yakov Bachevsky and colleagues, that he says that you have to group the samples by genetic horizons. That means that you have to know something about the soil to be able to group the soil together, similar soils, so that it can improve the precision. But nowadays, I think machine learning is very easy to use. That it's available everywhere. It's available on open source software. You can use it. And we have a proliferation of machine learning that you can use it for almost everything. And this is just some examples, not to try to mention anything, that there are hundreds of machine learning papers and applying to soil, applied to soil, that treat soil as a mathematical object or statistical object, right? So I start to ask that, do we really need in soil and soil water science in machine learning? Because if you look at any paper, if you look at a typical paper, you really don't need any soil science. Why do I say that? So because first of all, you need to get the data. There are lots of open data nowadays, and then you can do the pre-processing. You can clean the data, check for outliers, and then you can select the covariates. Nowadays, there's plenty of Earth observations data. You can download it. There's spatially, or either Google Earth Engine or anything. And then you can select it, and then you can train the model. You can make sure that the model is trained properly. You have the data split. You can tune the model. You can tune the hyperparameters. And then you have an independent test set. You test the model, and then later you can run some interpretation. You can run some sharp values and anything, and then that's it. But this flowchart, it's a generic flowchart that you can be used for anything. It's not just soil. It could be water. It could be environment. It could be air. It could be anything. So I asked the question, so do we really need soil and water science? As I say, the workflow is very straightforward, right? So there's a framework. You can even write a script that you just say replace replace your data here, that you got the data pre-processed, you select the covariates, you train the model using machine learning, what we call as the black box model, and then you can also interpret the model itself using different kind of interpretation. So I want to show you an example. I'm not trying to pick anyone. This is just an example. One example that is that we saw that are very numerous papers being published. It's about biochar. Biochar, as you know, it's a pyrolyzed organic matter. The material that has been pyrolyzed as a form of carbon that is resistant, and that has been used for many other things. So, for example, one of the application is that they use the biochar for pesticide absorption. So you take the biochar and then you take the experiment. Usually, you take the biochar from different things, and then you take you put it in a solution or put it in the soil, and then you equilibrate it with the pesticide, and then you measure how much of it is being absorbed. So this is a typical experiment, and there's hundreds of papers on it. And then there are hundreds of papers that says that you can use machine learning to predict the behavior of a biochar. So this is just an example, not to pick anyone, just an example that are very typical. You get the data preparation, you collect the data. It can be from the lab, it can be from the literature review. You pre-process the data, make sure the data fits, it's within the bounds and everything. And then you do the model development. You take the data, you split it into training and testing. And then you take the machine learning model, you make sure that it's tuned, hyperparameters tuning. You do the accuracy, and then the best model, you do the testing and so on. So this is again a very standard framework that you can use for anything. And this is just an example of the data. This is provided in one of the paper. I'll leave a few seconds for you to look. So this is the typical, for example, they collect it from literature that are experiments, the surface area of a particular biochar with some surface area, with some volume of pore volume of the water, and then the pH of the biochar, and then the contact time, how long it's been left in contact, and then either it's have some dose that you put in, and then the temperature, the initial concentration of the solution, and then how much it's being absorbed, right? So this is a typical data set that you see in this kind of experiments. And then you run the different machine learning. So this study run 3 machine learning, and then you get a best fit, and then you say that, and then you can run the importance variable, and then you can run the sharp value to see which one affects it, is it positive or negative, and so on, right? So this is all very typical, very straightforward, and you get a very nice prediction, and hundreds of paper and even thousands of paper being published at it. But what's the problem with this kind of data that I say? So I go back to this table of the data. If you see the table of the data, I'll leave a few seconds to see, maybe you can pick up what's the problem when we see that it's this kind of data, right? So this kind of data comes from an experiment, a particular biochar with a constant value, a constant pH, with a constant contact time and a dose. And then the things that only different are the concentration of in the solution and the absorption, right? So if we follow the procedure, that we do the split, we do the cross validation, and if we follow the procedure that we do a random split, that means any of this point that has a similar surface area, similar pH, got separated. Some of it is in a training, some of it is in a validation. And at the end, you get a very nice fit. And this is very common in biochar studies. And we even did a a review and we look at the papers that do these studies of biochar and the use of machine learning, we take the top cited papers. There are 64 top cited papers that has the very high citations. Some even got hundreds and thousands of citations. And if you look at even the sample size, even some paper only have 9 points, and they claim that they use machine learning to do these biochar machine learning studies, right? And what it says that 37% of the data, most of it has what we call as temporal or concentration-based leakage. That means that they are data that have a different concentration or different time and different absorption or different properties of the biochar that forms a curve, right? And then if you do this is, and most of this 92% is clustered data. That means clustered data. That means that it's from a particular studies that have a similar properties of a biochar or materials, the things that are varied. It could be a pH, it could be a concentration, and so on. And the problem is that, and a lot of the study has a very high test R square, 0.9. And so a lot of the problem is the data is split at the individual data point level. That means at a particular, this is, for example, the data set, they just randomly take half of it or 30% of it or 20% of it as an independent variable, right? So they are near identical samples from the same study that appear both in the training and the test set, right? So if we do this, if we do like a point study grouping, and this is just an example of 5 studies, if we do the grouping based on the split based on the point, you see that the R square, some of it is even reach 0.9 and so on. And if you split it based on the grouping, you can see that it really doesn't perform that well. And what it says is that random point splitting usually produce on average 80% higher accuracy than what it was meant to be. So all of these studies are completely useless because it's a pure mathematical, it's not a mathematical, it's a pure machine learning studies, data mining studies that doesn't have any doesn't know anything about the soil, doesn't consider the soil, doesn't consider the knowledge, and it's a machine learning studies that has no particular use because it's completely false, right? So we need to go back to this this workflow that says that this is the standard machine learning workflow, and start to put in some of this knowledge guided machine learning workflow. That means that we need to look at the data. We need to be, this machine learning algorithms need to be problem specific, and it needs to be soil science informed. So this is still the same workflow, but for example, in the covariates, that we can look at whether there's any real data, there's any augmentation data that we can use, any information that we can use to train the model. And for the problem specific soil science informed, is there any soil knowledge that we can represent in the modeling processes, in the covariate selection, in the model itself? And at the end, that the interpretation also needs to have some logical meaning, whether these models really perform, this model really has any useful meaning, right? So what kind of knowledge, what kind of information that we can put in this machine learning, right? So there are different things, like, for example, if it's to do with soil science or it's to do with the hydrology, it could be equations, for example, Phillips infiltration equations or the water retention curve equations. It could be a partial differential equations, the solving Richards water flow, Richards equation, or it could be a simulation results to guide the machine learning to replicate what it's meant to be, or it could be a general knowledge, it could be an expert knowledge, it could be a soil maps to say that this type of soil occurs in this area. It could be pseudo observations because we cannot survey, we cannot map we cannot survey everywhere, but we know for some sure that our expert knowledge that this area is, for example, is a pitland, it's a altisol or so, or general knowledge based on rules or probabilistic relationship, or it could be just a generic knowledge. And all of this can be embedded in the machine learning procedure or framework. It could be added as a probably of a training data as an observational priors, that because we know this already, it's not completely blind. Or it could be in the model structure itself, how we structure the model, or the constraint that we can constrain the model itself not to over predict, for example, water content beyond saturation, and so on. Or we could be a human feedback and final evaluation. All of these are possible, and all of these are possible to do, right? So going back to our biochar studies, is that this is kind of data, what is called a structured data. Some people say that it's to do with leakage, but having the guided knowledge guided that that in forming in reading the data, we should be able to say that this kind of data is a structured data, that a proper machine learning, if we want to do a machine learning, that means that you have to group at the study level, not at the point level, right? So, or you could summarize the absorption of the parameters of a curve, that it doesn't need to be so that it doesn't over-represent the data, everything. Or in linear models, it could be a mix of text model that take care of this kind of data, because each block of data, each type of biochar is they can be treated as a random effect. But because if we are use machine learning, because it doesn't have this kind of random effect, it treats every data points as the same weight, then you can have a problem of having this kind of over-representation of the data and overfitting of the data. And this kind of structured data is not just in machine learning or anything. It's also very common in meta-analysis nowadays, which I see. That meta-analysis, what does it mean? For example, we want to see the effect of some treatment, for example, biochar or cover cropping or anything to do with, for example, carbon content in the soil. So they take data from experiments in different parts of the world, from literature review, and then it's structured in some kind of way, like data similar to this structured data. That means, for example, an experiment or a study or paper, they have different rates of treatments, and then they have the results, right? So this kind of structured data is very common, and then they use machine learning to learn the data. And if this kind of structured data is presented to machine learning, it just treats every single line as a point, right? So this is problematic, but this can be solved by having a knowledge-guided machine learning, that you need to really know about the data and what it's about. So it's not a machine learning exercise. So I'll show you other examples where the use of machine learning, we can probably do a bit better than conventional machine learning. And one of my favorite topics is, of course, pedotransfer functions, that we've been doing this from the 1990s. Is that we have a basic soil information. For example, we have a particle size analysis, sand, silt, clay, bulk density, and then we want to predict water content at various suction point or various potentials. Or we want this is called the point pedotransfer functions, water content at saturations or at minus 100 centimeter and so on. Or we can predict the whole curve as well, what we call as parametric pedotransfer functions. If we can represent the curve as a water retention function. For example, the Van Genooten function, which is everyone knows and everyone use. Or maybe we can use the neural networks itself to predict the water content. The neural networks itself can tell us about the shape of the water retention, can predict the water retention curve, right? So we'll explore this. And going back to what Sarum mentioned, that initially this is what we call as parametric pedotransfer functions, is that we have a properties, for example, basic properties, particle size analysis, and so on. We want to predict the water retention curve, and the water retention curve can be represented as the function, Van der Nulten function equation. And it has a parameters, for example, residual water content, saturated water content, the air entry value, and the shape value. And in common machine learning, that means that the simple way is that we have the data, we fit the model, and then we train it, and then we fit it so that it minimizes, so that it can predict these parameters directly, right? So, but what we do is that these parameters sometimes doesn't have any physical meaning, but it can because it's a fitted parameters, is that we can also include the physics model in this these neural networks, in this formulation of the neural network. So because at the end, what we want to predict is the water content at different potentials. So what we can do is that these fitted parameters, we can put it in the physics model, and we can ask it to calculate the water content at the potential where it is measured. And that means that the loss functions is not just these parameters, but the loss function is actually what we try to achieve is we want to estimate the water content at a particular potential. So this is just a simple model, but we can also use it for more complicated model. This is just an example, scale Fred Sink and Wang model, which is nowadays people use. It looks very complicated. Why it's complicated? Because it tries to model water content at the as a function of the capillary and also absorption flow and absorption process, and also the film flow, right? Because it takes the water content from the saturation down to the dry end, or even at the zero water content, because conventional Van der Nulten parameters only fit it for a capillary, mostly for capillary water content, right? So this is a complicated equations, but we can still do it, and we can see that it fits better than the conventional Van der Nulten model. But we can also do the same thing, that we can use the neural network, predict the parameters, and then put it in the physics model, and then the loss functions is comparing with the observation of the water content. And even we take it further, that the optimized parameters, that we can use it to predict the hydraulic conductivity as well. So this is just an example that it doesn't matter what kind of model that we use, but if we can modify the loss function, if we can put some physics equation behind it, we can achieve greater accuracy, and all the parameters works better as well, because it respects the bound and so on. So this is just an example. I like it because it's a parametric model. I know the shape and so on. But then Saram, he told me that he wants to have a neural networks that doesn't have any parametric form. It can learn from the data. So we can put it in a neural networks, and then it can predict the water content. We can put the properties, basic properties, and we can put in the suction point, and then it can predict the water content. Just put in the neural network. So the concept seems very simple, but can we really use the neural network directly to predict the water retention curve? We don't need to impose any model on it. It sounds very simple, but of course it's not that simple. But we have to ensure that the model itself, the machine learning model itself, know the shape of the water retention curve. That it starts with the saturations at air entry point. It draws down monotonically, and then it should end up at the dry end, and it should end up at the for example, zero water content at PF7, for example. Right. So we can put it in the neural networks and let it train, but it doesn't respect any of the physics form. But in order for it to respect the physics form of the water retention curve, this is from Saram, that we have to put in some constraint and some additional data to force the neural network to know the shape of the water retention curve, right? So what Saram did is that, first of all, this is the neural networks, right? And then he also put in that the input could be the PF or the log of the suction, right? And the output is the water content at the particular PF and at the particular soil properties, right? So first of all, is to do with the minimizing the data loss, that this is the measured and the predicted water content at a particular PF or suction. He separated between the wet end and the dry end, just to make sure that the weight or the weight that the neural networks give to train the model, that because the wet end has a higher water content, because minimizing the loss function is always trying to minimize the larger value, so it will focus mostly on the wet end, but we need to also make it focus also that it also needs to focus on the dry end as well. So this one constraint, that is the data loss. And the second one is that we also need to make sure that the neural networks is monotonic. That means that it goes in one direction, so the water content could not be up and down. It should all, as we increase the suction, that it should always go that way. So this is built in the neural networks. But we need to also to make sure to tell the neural networks that it have to behave certain ways at the dry end and at the wet end. Then at the wet end is that it has a constant water content above the air entry head, between the saturation and air entry head. So it cannot decrease very rapidly. That in order to do that, it can have we put this constraint. And the second one is that at the dry end, at a certain PF, that it should linearly decrease. And then the pressure head at the water content, so that it should force it down to go to zero, that it cannot be negative or it could not be at a higher value and so on. So by doing this constraint, using the same neural networks, but rather than just fitting the data, we need to put a constraint, the physics constraints. So by doing the physics constraint, so Saram and colleagues have been able to recreate or to predict the water retention from saturation down to the dry end. And even at some points that where they have a limited number of data points, limited number of measurements, that it can still respect the water retention shape of the water retention curve, right? So even at some points, at some observation where we lack of the data, we can still use it for the training, because it informs about, for example, in this case, it's about the wet end, and in this case, it's about the dry end. And overall, this is what we can do with machine learning, that it's able to learn the shape of the water retention curve. I'll go to the next example, that in addition to be able to just learn the shape of the water retention curve, this is also by Saram, that can we also know the physics of this water retention curve? So for example, usually from a modeling point of view, if we want to go from X to Y, from something that from X to Y, that we need to know all these processes, right? All these processes. But in some cases, most of the time, we have a lack of knowledge of these processes. And in soil physics, if we have, if we know that this is to do with the water retention, is to do with the capillary and absorptions, but we really cannot separate it because this is going together, and also there's no one instrument can measure both. So and because of that, we replace it with parameters that characterize something. But in differential modeling, that we should be able to represent the concept that we have lag measurements, that we have no idea about the shape or the relationship with the neural networks or with a function, with the machine learning functions. So for example, this is, as I said before, so for example, water retention curve, it has the capillary component and it has the absorb component. And people usually model this based on some physical, have to assume the shape of the pore size and so on. And for example, this is the work of the Marcus Tuller before, that he has to assume certain shape of the pores to be able to differentiate which part of the water retention is due to the capillary and which part of the water retention is due to the absorption. So in this case, what Saram did was that he still used the pedo transfer functions and still the inputs and also the PF as the input. But this time, instead of one neural networks that model everything, that you can separate out different neural networks. One that models capillary water, one that models a transition function, and one that models this part, which is due to the absorption, right? So the capillary water retention function and this whole other parts are the absorption functions, which assumes that the water content decreases linearly at the dry PF and so on. And similarly, that rather than similar that to before, but rather than one whole pedo transfer, rather than one whole neural networks, you can split it into smaller neural networks. Then each of these neural networks model a particularly parameters or a particularly processor, particularly parameters. And also this is, again, that you can put constraint on the loss functions. So at the end, this is the water retention curve, which is measured. So we can only measure the water retention curve, but it can differentiate. It can try to differentiate which part is due to capillary, which part is due to the absorption. Then even it can measure the transition points where capillary becomes absorption and so on. So next one I will talk very briefly is about soil temperature, modeling soil temperature with space and time. It's a very popular topic. And again, there are various machine learning approaches, and even a high impact journal said they need to map the global maps of soil temperature with machine learning, right? So we have the data. The data is a space-time data. That means at a particular position, you had a measure of a soil temperature with time, right? So it's an easy example and it fits very well. The input is just air temperature, and then probably the remote sensing images or the soil texture and so on. And then you put it in the neural networks and it can predict the soil temperature as well. But what people forget is that soil temperature can be described and can be solved very easily with a one-dimensional flow equation. This is basic soil physics, which you learn in the undergraduate soil physics, right? So this is 1D heat flow. It's very simple and it's very easy to solve, and it describes very, very accurately about the heat flow and how temperature propagates from the surface down to depth below the soil, right? So it's based on energy balance. If you know the energy, if you know the temperature at the surface, you can propagate that heat down to the profile by knowing with this heat flow equation, by knowing the heat capacity of the soil, which is a function of how much water content is in the soil and multiplied by the heat capacity of the water, and the other mineral parts of the soil multiplied by the heat capacity of the soil. And the thermal conductivity, we can derive it empirically. This is just an example of how the thermal conductivity change with water content. As increasing water content, the thermal conductivity increases, right? So we can design this simply because what we have most of the data is that we have air temperature, which is collected roughly 1.5 meters above the ground. But we need to know about the land surface temperature. So because this is how the heat is arrived on the land surface, which depends on the land cover and so on, and the soil type. And then this is propagated. If we know the land surface temperature, then we can propagate that heat down to the profile. Right, so because we don't know the land surface temperature, we only have the air temperature. We could have a neural network models that model what is the expected land surface temperature if we have this kind of air temperature, we have this type of soil, and it occurs on this type of location. And this land surface temperature, we can it's just an intermediate value in the neural networks, which is passed through a 1D heat flow, because 1D heat flow is a very simple partial differential equation, which is very easy to solve and very stable, and you can solve it. You don't need to have neural network models to model it. Then you can have this prediction, but which minimize the data losses, minimizing the surface, the temperature as it propagates in the soil. So this is just an example. The dot points at one location, the dot points are the measured air temperature, daily air temp, not daily air temperature. This is the measured soil temperature at 10 centimeter and at 60 centimeter. And if we use the finite difference model, the physics equation directly, because we don't know about the land surface temperature, and if we use just the air temperature, it sometimes underpredict during summer, because the heat that goes to the surface of the soil is higher than the air temperature, and sometimes during winter it also can overpredict because of the air temperature difference. If we compare with the random forest model, it also cannot capture more of these nuances. But if we use the physics neural networks that model the air temperature, we can see, for example, here that we can model it more accurately because we try to predict the land surface temperature. And by doing that, we can models from air temperature, how it propagates into the land surface temperature at the soil temperature at various steps up until 1 meter 20 here, for example, in Tasmania. And this is the predicted value. So for example, and then the value, the profile that we have is consistent with the physics, because it's based on a physics model of a heat transfer from the surface down to below, right? So when we extrapolate it further to the whole of Australia, this is another study by another colleague, because the problem is that we lack all of these observations in various places. So if we use the physics-based model, calculated the heat propagation based on the soil type, based on the thermal properties that we can use, that we can see that it follows naturally the gradient of the air temperature, that you have a warmer temperature on the north of Australia and cooler down here, which follows the physics law. But if we use machine learning, this is, for example, surface vector or XGBoost model, that we can see some strange pattern here, that South Australia and the southern part of Australia suddenly have a higher temperature, which suddenly have higher soil temperature, which it doesn't, because it's an artifact because of the observations and so on. So that's also the beauty of the physics-based model, that it respects the physics and random whatever machine learning models. It's easy to use. You just put in the data and it spits out the results. Physics-based model, it needs a bit of tinkering, it needs a bit of modeling, but the results are consistent with the physics. Finally, I want to give a little spiel about what are some possible dangers of using machine learning in soil science, because as we say before, it's a black box and the interpretation is usually very difficult. And how to interpret it, even if you are interpreting it, there are sharp values, there are variables of importance, you are just sometimes reconfirming what it does. But having some kind of knowledge guided, hopefully that you can have a more knowledge guided interpretation. And the second one is that there are a lot of proprietary soil prediction at the moment. So various companies come up with various instruments to map soil, to measure soil, and so on. So those proprietary claim that they use AI and so on, but we don't really know what's going on. So if we believe this kind of system, then it could be problematic, because there's no transparency of how these predictions being derived. And the third one is that what we call as data science of soil materials. So if we treat as a materials, if we treat it as a data points in machine learning, that means that we can produce all this highly accurate prediction, which has no meaning and which has no use at all. And the next one is that if we keep trusting on machine learning, if we use machine learning for everything, that means that we generally we cannot come up with any new theory, because you are just self-confirming of what the data says. And many of the danger is that doing too much with too little, because it's very easy to fit a machine learning model, and then it's very easy to make maps of the world with 100 points, with 200 points, and so on. So, but we have to realize, but most of the time that those maps do not come up with the warning or with the limitations what it's doing. And finally, that if we believe that everything the data is available, that means that we don't go out and collect more data, which is probably not very useful if we keep relying on machine learning. And the next three things is more about AI, which I didn't talk about in this presentation, that now large language model or generative AI is it's being used a lot, and it's very useful. But sometimes if we rely on AI too much, then we can have a loss of foundational knowledge. And if we trust AI too much, that means that we could lose our creativity and even have some ethical risks. So finally, this is just my thought of about machine learning and its application. And currently in soil science, I say that some machine learning applications that really needs soil guidance. For example, meta-analysis, which I says that is currently being used a lot. It's easy to generate, it's easy to collect data from literatures. Even now you can use AI to collect the data for you. And then it's easy to put in the machine learning, but I think knowledge guidance about what kind of data is it in it, and that we don't overinterpret, we don't seek what we want to say. I think that is very important. And the second one is in soil mapping, that people want to make a soil 3D mapping. So the tendency that is very easy that you put X, Y, and Z as a covariate, as a predictor, but but we have to know, we don't know about the shape, what is going on, whether the machine learning can really learn about the pattern of the soil. So for example, as I mentioned before, the water retention curve, we can model the water retention curve because we know the shape, we know the physics behind it. But for the soil variation with space and depth, we don't have an idea. So because sometimes it's not monotonic, it can have a bimodal and so on. So trusting put everything to the machine learning, I think it could be a danger. And the next thing is the space-time modeling, because it's so easy to put space and time in the machine learning. People call it a data cube or whatever it is, but does it really model? Can it really model space and time? Because time in soil is a process. So as for example, soil temperature, soil heat, machine learning does not know anything about the heat flow. It does not model the heat flow. So it only models the pattern in the data. Right. So as a summary that for this presentation, I say that soil is a unique 3D volume, and machine learning models should be soil science informed about the soil. So we have to design the machine learning application that accommodate the soil, the nature of the soil. So that's why I say that it's soil science informed, that it could be the architecture of the model, it could be the variables that you put in the model, it could be the data layers. It should reflect the unique characteristics of the soil. And the next is that we have to modify the machine learning models to suit our needs, not modify our data to suit what the machine learning needs, right? So most of the time, we have these machine learning models. It can only take one input. It can only take whatever input it is. And we try to force our data into the machine learning model. I think we need to think that now there are machine learning models like neural networks, which are flexible, that you can design, you can characterize. I think it's better to have a more design the machine learning models than try to put your data to the machine learning model needs. And finally, combining machine learning and domain knowledge should provide more meaningful models in soil science. And most of this, what I discussed before, that it's part of a larger review. So if you want to see more examples of how we think that machine learnings can be informed by soil science, this is the paper. And thank you very much.